In section 1.6, we'll be talking about infinite limits and limits at infinity. So let's take a look at these two equations and the graphs, and we'll find these limits. So if we have a graph, that's usually the easiest way to find the limits, so we'll focus on those first. So this first problem asks us to find the limit as x approaches 2 from the left. So I take a look at x equals 2 from the left. I can see this graph is going to negative infinity. Now technically that does mean the limit doesn't exist, but if we're asked for a left or right limit, we want to be as specific as possible and say positive or negative infinity if we can. For the next problem, as x approaches 2 from the right, we're looking at the right piece. I see that that is approaching positive infinity. For the limit as x approaches infinity, so I'm looking at my right end behavior, x approaches infinity, I can see that that looks like it is approaching 2. It also helps that I have this horizontal asymptote drawn here, so I can see that for my limit as well. So again, that is right end behavior when it's asking for the limit as x approaches infinity. For the limit as x approaches negative infinity, looking at my left end behavior, that is also approaching 2. All right, see if you can try the next limits on your own for g of x. Okay, for negative 1 from the left, that is going down to negative infinity. For the limit as x approaches negative 1 from the right, we have positive infinity. For the limit as x approaches infinity, my right end behavior, I see that that graph is going up to infinity. Again, that limit technically doesn't exist, but we want to be as specific as possible. And for x approaches negative infinity, I see that my graph is approaching negative infinity. So we have special names for these types of graphs. The first set here on the left side, where we get infinity as our answers, those are called infinite limits. If you're taking the limit as x approaches a constant, like 2 or negative 1, and you get an answer of infinity or negative infinity, that's an infinite limit. And that really means that you have a vertical asymptote. For the second set, where we're taking limits as x approaches infinity or negative infinity, those are called limits at infinity. Sometimes, like for f of x, it tells us where our horizontal asymptotes are. So we have a horizontal asymptote at y equals 2. Other times it just gives us our end behavior. So this was a slant asymptote for g, but it could also tell us if we don't have an asymptote and the function is just rising or falling forever. So those last problems were problems that we've already done before. We've looked at graphs, we've found left and right limits and right end behavior. What we're going to do now is try to see how we do that algebraically. So this problem asks me to find the limit as x approaches 2 from the left of 2x squared plus 7x plus 6 over x squared minus 4. The first thing I always want to do is try to plug in the number. So I'm going to try to plug in 2. So 2 times 2 squared is 8. Plus 7 times 2 is 14, plus 6, all over 2 squared, which is 4, minus 4. That is approaching 28 over 0. This does not mean I can factor and cancel. That was if I had like 0 over 0. Whenever I have a number over 0, that's my format. That means I have a vertical asymptote. Now, knowing what you know from your graphs of vertical asymptotes, that tells me that my answer could be one of two things, either infinity or negative infinity. Those are my options. Okay, and so again, I know this because I got a number divided by 0, which tells me I have a vertical asymptote, which then tells me my limit is infinity or negative infinity. Let's try to simplify this and see if that will help us figure out which of those answers it is. So the numerator factors into 2x plus 3 and x plus 2, and the denominator factors into x minus 2 and x plus 2. My x plus 2's cancel, and so I'm really left with just the limit as x approaches 2 from the left of 2x plus 3 over x minus 2. Again, I could plug in 2 here, but I'm just going to get a number over 0. And so what I want to do is decide if this would give me something positive or negative. I know it's going to approach infinity because we said that up here. We've recognized already that it's a vertical asymptote. And so what I need to decide is which one it's going to. And so to think about that, I'm looking as x approaches 2 from the left. So I want to think about a number like 1.9. Now I'm not actually going to write this in, I'm just thinking about it. If I plug in a number like 1.9 to my numerator, I would get something positive. If I plug something like 1.9 into my denominator, I would get something negative. And something positive divided by something negative would be something negative. So my limit is negative infinity. We can do the same thing for the limit as x approaches 2 from the right. Now, already that's that same function. So I'm going to go ahead and use that simplified form. It's usually easiest if you use your simplified form. And now I'm from the right side, so I want to think about a number a little to the right of 2. So something like 2.1. And so if I think about plugging in 2.1, I would have 2 times 2 plus 1 plus 3, that's positive. And 2.1 minus 2 is positive as well. So my answer is positive infinity. Now again, I should have backed up here. It's similar to what we had before. If I would have just tried to plug in 2 first, I would have had a number over 0. A number over 0 automatically tells me I have a vertical asymptote, which automatically tells me my answer is infinity or negative infinity for a left or right limit. Okay, let's try the same thing for g of x. So that was x squared minus x plus 1 over 2x plus 2. If I try to plug in negative 1, I will get 1 over 0. Automatically, if I have a number over 0, that tells me I have a vertical asymptote. So I want to keep that in mind. I have a vertical asymptote. This doesn't really factor. The numerator does not factor, but the denominator does. That can still help us. If I plug in a number a little to the right of negative 1, that would be like negative 0.9. I would get something positive in the numerator. So my numerator is always positive. My denominator would also be positive. And so my answer here is positive infinity. Same thing for limit as x approaches negative 1 from the left. If I, again, just plug in negative 1, I'm going to get 1 over 0, just like I just did. So I, again, can look at my simplified form. And I'm thinking about plugging in a number a little to the left of negative 1, so I'm thinking about negative 1.1. And just to be clear, these are like little thought bubbles. This is just what I'm thinking about. You don't actually have to write this out when you're working out one of these problems, like on the AP test. So my numerator is positive because it's always positive. My denominator would be negative, so my answer here is negative infinity. So what you should notice is that these answers actually match up with my answers up above. And so this is just how we calculate these algebraically instead of graphically. So something that's important to realize is if I'm evaluating a limit as x approaches a constant and I get an infinite answer, so that's the infinite limit we're talking about, that will always yield a vertical asymptote. And if you remember back to pre-calculus, the way that you knew that you had a vertical asymptote was if you had a factor in the denominator that would not cancel out. And so from this point forward, that's not a viable justification for the existence of a vertical asymptote. So you can't say, oh, this function has a vertical asymptote because it has a factor of x plus 1 that doesn't cancel out. That's an okay way to find where the vertical asymptote is, but not an okay way to justify it. So let's talk about how we would justify it. So in order to justify the existence of a vertical asymptote, what we have to do is find the left limit or the right limit and verify that they are either infinity or negative infinity. So if the left limit of f of x is infinity or negative infinity, or the right limit is infinity or negative infinity, then we would know x equals c is a vertical asymptote. So that's our justification. You could still figure out where it is, like you did in pre-calculus, by looking at the denominators that don't cancel. But to justify, you have to write it with a limit statement. So we have to justify using actual calculus, which means limits. So let's go ahead and factor h of x. That helps us see what we're dealing with. The last problem's told us specifically where to find limits. This one we're going to have to figure it out on our own. So I'll factor the numerator. It's 2x plus 1 times x plus 3. And the denominator is x minus 1 times x plus 3. So based on your pre-calculus knowledge, you know that this factor, x plus 3, cancels out, which would tell you you have a whole at negative 3. And you would know that because this factor of x minus 1 did not cancel out, that you have a vertical asymptote at x equals 1. That's our pre-calculus knowledge. That would not get you full credit on a calculus problem. We have to justify using calculus. So we use this part here to figure out where the x value is, and then we'll justify using calculus. So just like up above, we're going to take the limit as x approaches 1, that's our c, from the left. And you can use your simplified form here. We've already said it's equal. And then we're also going to check the limit as x approaches 1 from the right. Now, if it just asks you to justify that there is a vertical asymptote, you would only need to do one of these. We're going to do both just to show you how it would work. So I know that there's a vertical asymptote, which means I know that this left or right limit is positive or negative infinity. So this one, I know if I think about a number a little less than 1, my numerator would be positive, my denominator would be negative, and so this is negative infinity. And so now I'm going to write my justification statement. Since the limit as x approaches 1 from the left of h of x is equal to negative infinity, then h of x has a vertical asymptote at x equals 1. Same idea for the right limit, limit as x approaches 1 from the right of 2x plus 1 over x minus 1. So a number a little bit bigger than 1, my numerator would be positive, my denominator would be negative, also positive, and so then my limit is infinity. And so I can say, since the limit as x approaches 1 from the right of 2x plus 1, let's say h of x there instead. Just relate it back to what we were talking about, of h of x is equal to positive infinity, then h of x has a vertical asymptote at x equals 1. Again, you want to make sure on these problems that you are actually saying that the limit is infinity or negative infinity where you can, and don't just write does not exist.